These are dark, dense cylinders made of a ceramic material. Each one is about the size of a peanut. This shows the energy density packed inside that single cylinder. One pellet produces the same amount of heat as 1,800 pounds of coal, or 150 gallons of oil. When German chemist Martin Heinrich Klaproth first identified uranium in 1789, he classified it as an ordinary heavy metal. For over a century, scientists remained unaware of the energy potential locked inside its atomic structure. This volume breakdown of natural uranium ore reveals the central engineering challenge. The vast majority of the block is uranium-238, an isotope that is stable and unusable for power. Only this razor-thin fraction, just 0.7%, is uranium-235, the isotope capable of sustaining a nuclear reaction. To fit the power of a coal mountain inside a peanut-sized pellet, we have to run raw earth through a massive engineering funnel, stripping away 99% of the material to isolate that specific 0.7%. The process begins in remote regions like Saskatchewan, Canada, home to some of the highest-yield uranium deposits on Earth. Here, the ore is trapped beneath thick layers of sandstone filled with highly pressurized water. If a drill pierces that layer, the entire mine would flood instantly. To extract the ore safely, engineers use a technique called artificial ground freezing. This involves drilling deep holes and inserting pipes that circulate chilled calcium chloride brine. As the liquid pulls heat, the groundwater freezes, creating an impenetrable ice wall that seals off the aquifer and isolates a dry pocket of ore so mining can proceed. Inside this frozen shell, remote-controlled drills break the rock apart. By using robotics, workers are kept away from both the radiation of the ore and the physical risk of a cave-in. Overcoming the pressure of the earth to retrieve raw uraninite is just the first macro-level filter. From here, we have to separate the uranium from the rock on a chemical level. The raw ore is crushed and ground into a powder, then mixed with water to create a thick slurry. Strong acids are introduced to the slurry, dissolving the uranium into a liquid solution, while the useless rock sediment settles at the bottom for removal. Once the uranium is purified, it undergoes a series of chemical reactions to turn the solid metal into a gas called uranium hexafluoride. By converting the rock into a volatile gas, engineers have finished stripping away non-uranium elements. Now, the final filter happens at the atomic level. To separate the isotopes, the uranium hexafluoride gas is fed into thousands of high-speed centrifuges. This diagram shows the physics at play. As the gas spins at supersonic speeds, centrifugal force pushes the slightly heavier uranium-238 molecules toward the outer wall. The lighter, valuable uranium-235 atoms stay concentrated in the center. Because this weight difference is microscopic, the centered gas must be extracted and fed into the next cylinder. This repeats across thousands of chain centrifuges, gradually increasing the purity of the uranium-235. During the Manhattan Project, this process was used to reach 90% purity for the atomic bomb dropped on Hiroshima. Modern power plants, however, stop at a much lower concentration, typically between 3 and 5%, to ensure the reaction remains stable. This enriched gas becomes powder, is compressed by heavy machinery, baked in furnaces for 24 hours, to form a hard ceramic pellet. This pellet is a distillation of thousands of tons of earth, processed and sieved until only the energy-producing isotopes remain. These pellets are stacked inside zirconium metal tubes. Zirconium is used because it can withstand the heat of the reactor, while allowing subatomic neutrons to pass through its walls without interference. The rods are bundled into fuel assemblies and lowered into the reactor core. Once the reactor starts, neutrons strike the uranium-235 atoms, splitting them and releasing intense heat and more neutrons. This blue Cherenkov radiation is the visual signature of that ongoing controlled chain reaction. This flowchart tracks how atomic heat becomes electricity. Energy from the core boils water into high-pressure steam, piped through to spin a massive turbine. The rotating turbine spins a generator, creating a steady stream of electricity powering the surrounding grid. A single reactor can provide baseline power for millions of people. By splitting atoms inside that tiny pellet, these plants produce energy on a massive scale with zero carbon emissions. After about a year of use, the uranium-235 is depleted. The pellets are now spent fuel, a byproduct that remains radioactive and thermally hot for thousands of years. These assemblies must be submerged in 30-foot-deep pools of water for at least a decade. The water acts as both a shield against radiation and a coolant to dissipate the heat. The pellet is a product of atomic isolation. By sifting a specific fraction of an atom from rock buried under flooded aquifers, we have created a power source that replaces an entire mountain of coal. But that density comes with a trade-off, a radioactive legacy that requires perpetual care.